For homework for part B, we're going to be starting with our process transfer function for 3 tanks in series, and then deriving our closed loop transfer function to calculate the height of our third tank with a proportional controller. So we'll be using block diagrams, so we'll make our transfer function a block diagram. Oh, it makes it a nice square. How nice. And this is going to be our GP, and what this is going to output is our height. So this will come back through our measurement device, which will just be 1 in this case, and go back up into here, which this will calculate our air. So we have our set point, our height set point, go to here, which will give us our air, which will then go into our controller, which in this case is just going to be KC, and this will be our GC, and then this will go back into our process transfer function, and this loop will continue. So what we see here is that our air times our GC times our GP is equal to H. So air times GC times GP is equal to H. And we know our air is calculated by our set point minus our height. So we can plug that in, and multiplying this out, we get HSP GC GP is equal to minus H GC GP equals H. We're going to move this across and pull out our H, giving us, and then we'll also divide across by our GCGP, just giving us our HSP is equal to 1 plus GCGP over GCGP times H. And we want to have, since we know our set point, we want to move this over to the other side, giving us our final equation, which will be H is equal to GCGP over 1 plus GCGP times our set point. We know our set point to be our amplitude, so if we have our set point here and our initial state, we know this distance will be A, or any variable we want to give it, and then it will all be over our step time, our S, so our HSP is equal to A over S. And we can also plug back in our KCs and our GPs, giving us H is equal to our GC, so KC, times our K over tau S plus 1 cubed over 1 plus KC K over tau S plus 1 cubed multiplied by A over S. We can now, we're going to simplify this more. So our 1, we're going to get a common denominator of tau plus 1, or tau S plus 1 to the third. So we'll move all of this around, giving us KCK tau S plus 1 cubed over tau S plus 1 cubed tau S plus 1 cubed plus KCK over tau S plus 1 cubed. Meaning all of these will get canceled out, leaving us with just H is equal to kck over tau s plus 1 cubed plus kck times a over s. Now what we can do is multiply our tau s plus 1 all the way out. So that will give us tau cubed s cubed plus tau squared s squared, 3 of those, plus 3 tau s plus 1 plus kck over or under kck times a, and this is all multiplied by s. And this is going to be our closed loop transfer function to determine the height of our third tank level. For the next part of homework for part B, we'll be using our Roth-Howitz and our closed loop transfer function in order to determine what value of Kc will result in a stable or unstable process. So our Roth-Howitz, we have our table and how to calculate our B's and C's, and we will now take our process transfer function, our closed loop, and plug in our values for that. So we'll be using our S as our ANs, so we can now begin to transfer our values into there. So S cubed, S squared, S to the first, and then this 1 plus Kc can be thought of as being multiplied by S to 0, or just 1. So we'll begin to plug these in. So our AN is going to be tau cubed. Our AN minus 1 will be 3 tau cubed. Our AN minus 2 will be 3 tau. And lastly, our AN minus 3 will be 1 plus kck. So to get our first B, we go AN minus 1 times AN minus 2. So we'll have 3 tau squared times 3 tau minus our AN, so tau cubed, multiplied by 1 plus kck. And this is all over 3 tau squared. So this will cancel out, this will cancel out here, giving us just 1 tau, and then we'll be left with that 3 will also get canceled out there, but we'll still be over here. So our first B is going to be 3 tau minus 1 plus kck times tau over 3. And then moving forwards, in our situation, these next values are going to be zeros. So we'll move over, giving us a 3 tau, and then these will end up getting multiplied by zeros, giving us a 0 as our next B. So moving on, for our C, we will put in our Bn. We can see that that will be our 3 tau minus 1 plus kck over 3 times tau multiplied by our Bn, or not Bn, our An minus 3, so times 1 plus kck, and then we have our An minus 1 and our Bn plus 1, so our Bn plus 1 in this situation is 0, so this will be minus 0 over here, and then this is divided by our Bn, which is just 3 tau minus 1 plus kck over 3 times tau, and these two will cancel out, leaving us with just 1 plus kck. again, this one will end up, terms will cancel, get multiplied by 0, giving us 0. So the next thing we can do is we can notice that in order for our stability analysis of this system, it's based upon the sign of these not changing. So we know that our 1 plus kck will always be positive, and we also know that, well, that leads us to the conclusion that our 3 tau minus 1 plus kck times tau over 3 must be greater than 0 in order for no sign changes to occur, meaning our system will be stable. So we can move this down to our 3 tau minus 1 plus kck times tau over 3 is greater than 0. So we can move this to the other side, giving us 3 tau is greater than 1 plus kck over 3 times tau. We know that our tau will always be a positive value, so we can divide across and not worry about switching our signs. We can then multiply by 3, giving us 9 is greater than 1 plus kck. We can then move our 1 over and divide by k, giving us 8 over k is greater than kc. So for our system, our k will be defined, meaning that our kc must be less than 8 over k in order for our process to be stable. So now the next thing we'll do is go to Python in order to see if our analysis is correct. For the last part of homework 4, part B, we're going to be simulating our system to see if our analysis of our limits of kc are correct. So what we're starting with is our k value for our transfer function, our tau value for our transfer function, and then our set point step size, our a. So what we need to do now is define our GC and GP and then our closed loop function. So our GC is going to be our process transfer function, which is k divided by our tau times s plus 1 cubed, and then our GP in this case is just going to be equal to our kc value, which we will call 0.5 for now, which should be below our stable limit. And then we need to create our transfer function for our closed loop, which is just what we derived earlier, GC times GP 1 plus GC GP. So our loop, we'll call it, is equal to GC times GP divided by 1 plus GC times GP. Now we'll get our function, so our times and our heights will be our simulation of our function loop. Our lambda time variable, our number, or our a value, our number of steps, so we want 1,000 steps, and our time step, which is going to be 1, and I didn't run this, I also need to run this. Run. Okay, so we've ran those. Now we can go back. Invalid syntax. We don't need a comma after the colon. So that ran, so now we can make our figure. Make subplots. Fig dot add scatter. Our x values will be our time, our y values will be our heights, and our name for this will be height. H-E-I-G-H. Height. So as you can see, our system is stable. It converges to 0.1, which it would represent our set point. And so if we make this lower, there should be no problems. But as we approach our value, so we know our k is 12, and that our limit for our kc is going to be 8 divided by k. That means our limit for kc should be approximately 0.667. So once we reach that number, our system should no longer be stable. So as we get closer to that, we should see a little bit more oscillation, and then even closer, more oscillation, but it still remains stable. But once we cross over that threshold, we see that our system begins to grow in our oscillations, and just increasing it even a little bit more, it will start to grow very, very rapidly. Okay.